Assalamualaikum warahmatullahi wabarakatuh. Today our group, which is group J, will present about flow through duct. So here we go. I will introduce all of you about our group members and task allocate to each of them. So first is Muhammad Aika bin Noh. He will explain the theory related to the topic and the problem need to be solved in the simulation. Next is me, Muhammad Akmal Irfan bin Sudarmin, which I will show the geometric details and dimension and allocate tasks of each group members and compile the presentation. The third is Muhammad Iqmal Adam bin Muhammad Alfian. He will execute the simulation and explain every step clearly. And last is Muhammad Izrul bin Maizani. He will explain the result and relate the result with the theory.
In this presentation, we will teach you how to conduct fluid flow and heat transfer analysis in a rectangular duct using ANSYS Fluent. The objective of this experiment is the design to lower the pressure drop and visualization of the flow pattern inside the duct band. Other than that, this experiment are to measure the force generated by the air moving through a curved rectangular duct and to test the validity of a control volume analysis based on the linear momentum principle. Lastly, we will find out whether a straightforward idealization can accurately represent the tangential velocity of the airflow in the band. Next, we will discuss about the simple theory of flow in a band. Using pressure taps along the walls to produce the pressure distributions, we explore the flow around a 90-degree band in a rectangular section duct in this experiment. The flow is depicted above as having a uniform velocity u as it approaches a band. We will assume a free vortex distribution of velocity within the curve, given by u equals to c over r, where u is the streaming velocity at a distance of r from the band center of curvature. The equation of continuity can be used to determine the constant c as follows here, where b is the duct section width. After we do an integration of this equation, we will have the velocity distribution as follows here. Assuming that Bernoulli's equation can be used to determine the pressure distribution between the upstream part and a segment inside the band, the following equation can be done here, where P is the pressure at radius r in the band and P0 is the static pressure upstream. It is common to define P as a dimensionless pressure coefficient, denoted by the symbol Cp, where the equation here can be seen. This equation may be also written as this equation. By substituting the proper value of u over u obtained from the equation, which may be assessed for any radius r, as demonstrated, a comparison with measured Cp values can be established.
So I will continue to my part, which is geometry details and dimension. Okay. So this is the dimension and geometric details. We can see there are top view, right view and bottom view.
This is the step-by-step tutorial on how to use ANSYS Fluent. First, we import the geometry file. Then right click on the geometry and select edit geometry in space claim. Click on Prepare tab, select Volume Extract and click on Select Edges. Select the edges from outlet and inlet of the duct, then click Check. Close the window. Right click on Mesh and select Edit. Expand geometry and right click on the FFF, then select Suppress Body. Right click on Mesh and insert sizing. Change selection mode to edges. Select 4 edges from outlet of the model, then apply. Change the type to number of division and put value of 50. Repeat the same step for inlet of the duct, then generate mesh. Insert inflation and select the whole model. Then select the outlet and inlet as boundaries, then generate mesh. For mesh metric, select skewness. Here we can see the mean, max, average and standard deviation values. Create name selection for inlet, outlet and wall of the duct. Close window, then update the mesh. Right click on setup and select edit. Tick double precision and enter the value of 4 and 1. Select units and change the temperature unit from Kelvin to Celsius. Press list, then close. Ensure energy equation on and viscous model is K omega NSST. Select inlet and input 5 for velocity and 16 for temperature. Select wall, then change thermal condition to temperature and enter value 30. Select methods. Ensure the scheme is coupled and all the force except pressure in second order upwind. Check pseudo tension. Select initialization, then initialize. Select run calculation, then enter 200 in number of iteration. Then check case before clicking calculate. A graph will be generated once the calculation is complete. Close window. Right click on results and select edit. Insert contour and select inlet, outlet and wall, then apply. Repeat the same step but change the variable to temperature. Insert volume rendering and select texture of white metal, then apply. Repeat the same step but change the variable to temperature. Uncheck and check the boxes to examine the result of individual pressure and temperature. That is all. Thank you for watching.
I'm Muhammad Izrul bin Muhammad Izani, and today I will explain about the result and explanation. From the result, the maximum pressure for contour 1 is at the inlet, which is 1.492, and the minimum pressure is at the outlet, which is -1.759. Is about the temperature, where the maximum temperature is at the wall, which is 3.031, and the minimum temperature is at the inlet, which is 2.891. Of the volume rendering 1 and 2. The flow pattern for volume rendering 1 and 2 change through the duct. The direction and amplitude of the rotation vector cause the secondary flow. From us, thank you.